lecture with the formate ion. So hopefully you guys, you see how I kind of have them going across horizontally, but for you guys, they're vertically. So go ahead and find this, one of these sheets, okay? And at the top of them, go ahead, at the top of that sheet, go ahead and put what you're going to be, I'll tell you what we're going to be doing, okay? But this is what the sheets look like. Let's see. Yeah. We got it. So basically, horizontally, we go steps 1 through 5, and then also down, we have these checks. Okay, and we'll talk about each one of those checks. I just think I'd just like to jump in and do an example. So at the top, if you don't mind, put NH3, ammonium. Okay, so that is the molecular polyatomic ion that we're going to draw first. And after we draw it, you guys are going to make I have these little molecule sets up here for you guys to do. Okay, so this is like we did with the formate ion in class. You're going to need a periodic table, but the first step, so in the first box, you need to come up with those 3 atoms, the nitrogen and, 4 atoms, the nitrogen and 3 hydrogens. What is the pot of valence electrons? So I would take 1 times, for nitrogen, I usually put N colon 1, because there's 1 nitrogen atom, times 5 electrons, because it's 5A. And then underneath that, I put hydrogen. There's 3 of them, and they each have 1 valence electron. So you're looking at a grand total, if you can read my writing, of 8 electrons. Okay, so that goes in the first box. Now, you're going to have to put something in the middle, and I told you yesterday, hydrogen never wants to be in the middle. And then aside from that, you go low electronegativity. So you're going to have to put nitrogen in the middle. So in the next box, you know, it's not all that complicated. We simply draw the preliminary Lewis structure. Nitrogen with the 3 hydrogens sticking out from there. Now, those dashes, of course, those are primary sigma bonds, right? And each dash represents, what, 2 electrons. So there, I think in that same box, okay? So there what I do, maybe in that box or maybe in the next box, is I do a little subtraction. It's hard to read my own writing, but that is an 8 minus 6. The 8 represents the pot of electrons we started with, and the 6 represents how many are represented on that preliminary structure. So 8 minus 6 is 2. So that's the 2 electrons that we can do something with. Now, usually, in all of these kind of before, let's see, a few pages, they're so good, just marking your stuff. At the very beginning of this lab, it gives you kind of instructions for each one of these steps. So the next step is to take those 2 electrons and put them around terminal atoms. So the terminal atoms are hydrogens. Do they want any more electrons? No, they're done. If they're done, go ahead and take those 2 electrons and give them to the central atom. Does nitrogen want them? Yeah. So actually our step 4 simply looks like this, where we go ahead and redraw the preliminary structure, and we put those 2 remaining electrons, ... next to the nitrogen. It makes sense, right? Now, step 5 may or may not apply. Step 5 is about the central atom. It said if the central atom does not have a complete octet, swing lone pair electrons in from a terminal atom. So I would put Na there. It does not apply. Okay? Look good? So we continue down, okay, and we've got a couple of sections. For each of the Lewis structures you draw today, okay, you're going to have to do these checks. First off, on that final Lewis structure under step 4, how many electrons are there?
It's like a total of 8.
I'm getting 8 also. Yep. Okay, so that matches. Yep. Let's see. Does each...
But yes.
Yes. Yep. What is the... Oh, I guess I would put 8. What is the total number of electrons? So I'd put 8.
Okay.
Yep. And so make sure that these match.
Okay.
And
So
the...
8 equals 8.
8 equals 8, yep. Do they each have a rare gas configuration? How about nitrogen and hydrogen, hydrogen? Yep.
Yep. So they both have the octet.
Yep. Yep, they both have, the nitrogen has an octet and the hydrogens have a duet, which is like helium. So is this a neutral molecule? Mm-hmm. Yep. Okay, so if it's a neutral molecule, are the atoms following their expected valence rules? Now, yes, they are. I'm going to go ahead up here and add something. Okay, and it's something that we talked about, I think it was yesterday in lecture. I get my days mixed up. But the expected valence is the number of sigma and pi bonds you expect an atom to extend. So valence of an atom, and it only works for neutral atoms. Valence of an atom is equal to 8 minus the group number. GP for group. Okay. So here again, you have to have a periodic table because maybe you do. Oh, there's a periodic table in here. Maybe you do, maybe you don't. But nitrogen is 5A, so 8 minus 5 is 3. So you expect it to reach out 3 times. And actually, these 3 times actually are 3 sigma bonds. But they could be sigma or pi bonds. That's the expected valence. So sigma and pi bonds. Okay. All right. So that's looking good. Oh, hydrogen, what's its valence? Do you remember?
2.
Nope.
1.
1. Yep. Yep, very good. Okay, so now that last part, we have to, it's a set of questions about the central atom. So which atom's the central atom here? It is nitrogen. So this right here is what I put, you guys have this, I think, as a slide in your background information, okay? This table is what can help you with that last part. We talked about structural geometry around an atom. What do you need to focus on? I said sigma bonds and lone pair electrons. We talked about if you're looking at the Lewis structure, kind of evaluating it, if you count sigma bonds and lone pair electrons, then you know hybridization, orbital hybridization. Okay, and then you also know the structural geometry and you know the bond angle. So this is all questions about one atom. It's not about the molecule. Okay, so nitrogen, how many sigma bonds around that nitrogen atom?
Is there only one?
There's 1 lone pair electron, but how many sigma bonds?
3.
There are 3, yep. 1 lone pair electron, 3 sigma bonds. So my math is not great, but we're looking at 4, okay? So you're going for that third, everything in that third row is appropriate. Because you got 4 there. Okay, so you can fill in all that junk. So hybridizations, sp3, structural geometry.
We trigonal.
No, it'd be tetrahedral. Yep. sp3 means it's got 4 things scattering, and in a minute you're going to convince yourself what tetrahedral really looks or feels like. And then the bond angle is 109.5. So here's where we're going to make those, or you're going to make those, is dun 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 dun, H2CO. So go ahead and in that first box, and you can kind of see what I did in that first box, your pot of valence electrons. Actually, for my intro students, that's on their test, and I don't know if I do it for you guys too. I don't think so. I think I just make you draw the Lewis structures. But coming up with how many electrons can be on your final Lewis structure is very important. So you'll do 2 times 1 for hydrogen, 1 times 4 for carbon, 1 times 6 for oxygen, and I get 12. And sometimes, honestly, when you guys will have some more practice at doing these, you might just do the pot of valence electrons and kind of figure around with your atoms, and just make sure that on your final Lewis structure it matches this and it follows the expected valence rules if it's a neutral molecule. Yeah. So now hydrogen won't be central, carbon or oxygen, and you see which one's lower electronegative. Carbon's less electronegative, yep. So carbon's going to be in the middle. So then the preliminary structure looks like this, with carbon in the middle, dash hydrogen, dash hydrogen, dash oxygen. So now your homework, sometimes they kind of deviate from this central atom, but on your test, This technique will always work for you. You'll have something in the middle that's least electronegative. Hydrogen's never in the middle. So let's see, how many electrons do we have left over?
6.
I got 6. Because we had a pot of 12. I'm showing 6 electrons there on my preliminary structure. So I have 6 electrons to distribute around the outside or terminal atoms. 6 electrons. So, does hydrogen want any more electrons?
No.
No. How many more electrons does oxygen need?
6.
It needs 6. So quite honestly, that next step, step 4, is going to look just like we're going to fill the oxygen first. Okay? So that's also kind of an intermediate Lewis structure. Does that work for everybody? So now what's wrong with carbon though? How many electrons does carbon have?
Only 6.
It just has 6. So this is what we did with formate. I think we did this formate.
Never mind, I have something wrong. Boron that can have 6.
Right, that boron 6. If that was boron, we'd stop now. Yep. So we're going to have to swing one of those pairs of lone pair electrons in and make a pi bond, a secondary bond. And it doesn't matter which one you swing. Okay, so those 2 electrons came in to make a secondary bond. And the cool thing about that is the oxygen still has joint custody because it needs it to be an 8. And now the carbon now went from 6 to 8 electrons. So now the carbon has 8 electrons around it. Okay? All right. So how many electrons on our final Lewis structure?
12.
I got 12, yep. Does each one of those atoms have a complete octet or rare gas configuration? Yep, I think so too. Carbon has 8, oxygen has 8, hydrogen has 2, so I'm good with that. So since it's neutral, let's look to see if all of the atoms are reaching out the right number of times. Reaching out, I mean sigma and pi bonds, okay? So carbon is 4A. We'll find carbon on the periodic table, 4A. So 8 minus 4 is 4. Is it reaching out 4 times? Yes. Okay, oxygen, find on the periodic table, is 6A. So 8 minus 6 is 2. Is it reaching out twice? Yeah. So that's all good. Cool. So we need to answer these questions about carbon. So carbon, how many sigma bonds are extending from that carbon atom? There are 3 sigma bonds. How many lone pair electrons? Lone pair electrons around carbon. None. Yep. So we got 3 plus 0.
Which question is this on here?
So this is
getting
actually,
confused.
this is coming up with that whole set of 3 questions. But in
Okay.
order to answer that set of 3 questions, I'm going to go to this table.
Okay.
Yep, that's first column on this table. And the first column says sigma bonds and lone pair electrons. So I got 3 plus 0, so I got 3. So I'm going to go with that middle, that whole middle, this right there. Okay, so it must be a trigonoplanar sp2 orbital hybridized and a bond angle of 120. That's all the things we can say about that carbon atom.
Wait, why are you doing the middle one instead of the last one?
Okay, because we don't count pi bonds, so it's just sigma. Yeah, and in a double bond we have a sigma and a pi. So we have sigma, sigma, sigma. And the pi doesn't count for, and you're going to see this maybe when you make this molecule with your models. Yep.
When I was trying to find out where we were, I skipped one about, is this a neutral molecule? Yes?
Yes, it's a neutral
Okay.
molecule, and that was the one where we said the expected valence is correct because carbon's reaching out 4 times. It's group number 4. 8 minus 4 is 4.
Oh.
Oxygen's reaching out twice. It's 6A. So 8 minus 6 is 2 twice. So it's right. Okay, so go ahead and make those structures. We got, for the next line, Alright. So on to the next page. Oop. Fast forward, blah, 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 blah. Okay. The next one is everybody's beloved polyatomic ion, ClO with a -1 charge. And hopefully you guys are memorizing these. That is the set of halogens that we use the hypo prefix and the ite ending. So that's hypochlorite. That is hypochlorite. So, pot of valence electrons goes like this. We have 1 times 7 for chlorine, because it's 7A element. And for oxygen, we have 1 times 6, because it's a 6A element. And then just like we did in the example in class, since it's a -1 charge, we add 1 electron in. So 7 plus 6 plus 1 is 14 electrons. It's really common to make a mistake with these adding these whole numbers. You are a very good company if you make a mistake. Okay, so I know it doesn't make sense to say what's in the middle, okay? But I think, I think I go with chlorine in the middle. I can't remember. Nope, I'm going to play a game the right atom, which is oxygen, I'm going to call that the central atom, just for kicks, if that's okay with you. Okay, so my preliminary Lewis structure looks like this, where I just draw that sigma bond connecting the 2 atoms. So I've used 2 electrons, so how many do I have left over? 12, exactly. I have 14 minus 2 that I use, so I have 12 electrons left. Okay, now I told you we're going to put them around not the central, but the terminal atom first. So we'll put them around the chlorine first, and then we'll put them around the oxygen if we have room. Okay, but like how many electrons does the chlorine need?
6.
It needs 6. How many electrons does the oxygen need? It also needs 6. Can we do that with our 12?
Yeah.
Yep. So you got it. So basically, step 4 looks like this, where we have chlorine, sigma or single bond, oxygen, and then we have 6 electrons in pairs. So dot, 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 3 pairs of lone pair electrons around each of the atoms. Yay! And I'm thinking step number 5 is Na, not applicable. Because if we did go ahead and say oxygen was our central atom, it's got a complete octet, so we're done. So step 5 is not applicable. Now, one last thing, I mentioned this in class, that you have to, does anybody remember what we need to do to this in order to get full credit?
Like brackets?
Yes, brackets with a little charge outside, exactly. So to get full credit, you got to do that, which to me kind of makes sense. Okay, so we went with oxygen as our central atom, so I guess those are the green checks at the bottom. But before we get there, how many electrons do we have on our final Lewis structure?
14.
We have 14, so that's good. That check is wonderful. Do the chlorine and oxygen both have 8 around them? Yep, I agree. Okay, is this a neutral molecule? No, it is not. So if you want to, in that box, if there's room for that check for expected valence, that's not applicable, okay? Just for kicks, though, let's say it was applicable. Oxygen, we said, should reach out how many times? What's expected valence of oxygen, remember? 2. It is, yep, because it's a 6A. 8 minus 6 is 2. You know, it's not following its expected valence rules, but it's not a neutral molecule, so that's fine. Okay, so let's answer the questions at the bottom about oxygen, about its structural geometry. Now, sometimes I'll say students, but we have a hard time thinking of those electrons as giving geometry around that oxygen atom, but they do. So, how many sigma bonds extending from the oxygen atom? How many sigma bonds? 1. Yep. How many pairs of lone pair electrons extending from the oxygen atom?
3.
Yep, 3. So, which row do we go with? We have 3 pairs of lone pair electrons and 1 sigma bond.
Linear.
SP3.
Yeah, we go with that last row, exactly. Because that last row, that number over there is 4, and that matches up with this 4. Yep. So that's the 4, and so we go along the bottom. So now we know, can answer questions about its hybridizations to SP3, structural geometry, tetrahedral. Okay. Now bond angle, if you put 109.5, I probably would put 109.5. But as it turns out, the bond angle actually is not applicable in this case because it's not at the vertex of connecting to two atoms. So it's really kind of, 109.5 is fine, but really it's not applicable. Okay, so let's go ahead and make that structure. So basically we've got to go 2 times what?
7.
2 times 5, yep. 2 times 5, yep. So I get 10. That's it, that's our pot. So the next box just looks like N sigma bond N. So how many electrons do we have remaining? 8, yes. So we have 8 electrons. And I think what I'm going to do, again, is like what I did before. The one on the right, I'm going to call that the middle, the central nitrogen atom. Because now it does kind of make a difference. I'm going to go ahead and make that left one, I'm going to give it an octet first. How many of those 8 does it want? It needs 6. So I'm going to redraw N sigma bond N. I'm going to put 6 of my 8 around the left nitrogen. And I'm going to put 2 around the right one, which would be the central nitrogen atom. Now, step number 5 does apply, right? Because how many more electrons does that right nitrogen need?
4.
It needs 4 electrons. Yep, it's only got 4 now. It needs 4 more. So we're going to have to swing in 2 lone pair electrons. Or we're going to make the screen go black. Okay. So I swang them from the north and the south, and in this box then, it looks like what? So between the nitrogens, we have the sigma bond, and now we have pi, pi. Okay? So we have what? That's a triple bond. Nitrogen, triple bond, nitrogen. What was left on the terminal or outside nitrogen? Well, 2 electrons that we didn't swing. What was there on the central nitrogen? Well, 2 electrons that were there from the pot. Okay. So let's see. How many electrons? How many electrons do we have represented here in our final Lewis structure? 10. Yep. 2, 4, 6. Wait. 2, 4, 6, 8, 10. Yep. I'm liking 10. Now, does each nitrogen have a complete 8 around it? Because they're sharing 6 electrons, and they each have 2. So, yep, 6 plus 2 is 8. 6 plus 2 is 8. Yep, they both have a rare gas. Is this a neutral molecule?
Yes.
Yes. Since it's a neutral molecule, how many times what's the expected valence of a nitrogen atom? Expected valence. It is 3. How'd you get it?
5 minus 8.
Yep. 8 minus 5. Yep, got 3. So, now remember that is sigma and pi bonds. So is nitrogen reaching out sigma and pi 3 times? It's reaching out once sigma and 2 pi. But in that case, we add those together for the valence. So yes, 1 plus 2 is 3, and that's working. So yes. What's that?
I skipped ahead.
Okay. Okay. Yeah. It is confusing because the valence is sigma and pi bonds, and the shape is lone pair electrons, sigma bonds. So okay. So around either nitrogen, because they're symmetrical, but around this right nitrogen, how many sigma bonds do we have here? 1 sigma bond. How many pairs of lone pair electrons? 1. So, of course, 1 plus 1 is 2. So that's where we go to this table, and it's all about 2 then. Okay, so what's its hybridization? SP, yep. What's its structural geometry? Linear, yep. And what's its bond angle? 180. So that's how that works. So go ahead and make that molecule. Very good. Make that molecule. Sorry.